Welcome everyone. Today we are going to solve the Codeforces problem D1 and D2 of round 740. Both the problem statements are same, only varies in constants of n. So first I will explain the D1, then with this some small changes we will solve the D2, that is the other version of this problem. So now I am going to explain the problem statements in a quick way. So here we have given an integer n, which is the vertical strips cells, and first I am explaining for D1, and we have to find the number of ways to reach a cell 1, means we have some vertical strips. Let me draw. And let we will be some x. Then we have to count the number of ways in which we can move to cell 1 from particular cell n, that is given in our problems, and we have allowed only two different movements, that is one is we can move to any of the chosen integers y in range 1 to x minus 1, and second movement we can do is choose the integer z from 2 to x and divide by x, and the cell we are reaching, it will be count, means we are at, for example we are at 6 and we choose z equals to 3, then 6 by 3 equals to 2, then this will be, we will be at 2, and from 2 we choose the y equals to 1, then we will be move at 1. This will be count as one movement, and second movement we can do is choose y equals to 4. So we will go at first 4, and from 4 we will choose z equals to 4 and divide its floor division, we will reach at 1. So it will be count as the second another movements, and similarly this step will be follow. So we have to count the total number of different ways we can reach at cell 1 from a particular cell n. So simply after saying this, we can easily say it's a dynamic programming problems with some optimization. Now see the optimization we have to do, and if the problem is simply about counting the steps, we know that one problems in at coder we have solved frog jumps, that the basic DP problems we are solving, but the twist here is we have also given second method, which is x divided by z to reach some index I, and we have to also consider this. So simply our DP transition state will be like that: dp I equals to summation j equals to from 1 to I minus 1 dp j plus summation z equals to 2 to I dp I divided by z. Now this will be of n square, but our n is too large, so we cannot do it in n square. So we have to see some optimization in this. So first I am showing the code without optimization to generalize you the problem more clearly. And dp equals to 1 is our base case, that only one method will be there if we present at the cell 1 that we have to reach. And for the further transition from I equals to 2 to we are running till end first loop, and in the second loop we are choosing the y's from 1 to x and summing the dpi plus j. And for the floor divisions we are doing that the floor division that I have told the second transition, and this will be pass all the cases, all the test cases, sample testers that is given in our problem, but we are given to in 10 to the power 5, so we are getting TLE on 5 test cases, which is pretty large. So now I am going to explain its real solution. So now we are moving to the optimizing these two parts of our DP. First is linear summation and second one is floor division summation. So first optimizing the first part, that pretty sure that you have done in previous DP problems. Let we have n equals to 13, and for this dp sum we generalize that dpi equals to summation of j from 1 to I minus 1. So we can write this first movement as dpi equals to dp I minus 1 and dp of summation from j equals to I minus 2, and we can easily see this is simply dp I minus 1. So our dpi will be simply the summation of, and we can store this sum as the prefix sum that I will show you in my solution. So let's move to the solution. Further it will be more confuse you. See, in the first where prefix sum I am storing, assigning the prefix sums for the different previous I that I am calculating here, and simply storing this prefix sum I am getting for each I in O1 time. This is simple. So let's move to the second difficult transition, flow transition type. So in flow transition we have observed and pattern that for the repetition of the number whenever we dividing, it's a finite number of counts and will have some patterns, and the patterns is something like that. If we take I equals to 13, and for this the j will be from 2 to 13, then after dividing we are getting 30 divided by 2 6, 30 divided by 3 4, and similarly for 7 and 13 we are getting 1 and this. And why this is happening? So for this we have to come to the definition of the floor divisions. So in floor division, x by y equals to sum I, then I will be range less than I into y less than equals to x. This is the division of floor. So the x can maximum goes up to less than I plus 1 into y. So our x will be something in range I into y into I plus 1 into y minus 1 in exclusive range. So from this we can observe that we can definitely measures the range of the particular I, that how much counts of the x we can get for that particular I. So from this we can easily generalize our dp, and we do not have to count this all the times, and we can see that for a particular n, if we try to generate more cases, the maximum repetition can go up to root I, which is 13 root 3. Then from 3 we can show after the 3 repetition will be stop. So this give an idea to run the second floor division loop till root n, which is pretty good for this dp transition. So let's move to the dp solution. See, simply I have first set my prefix sum equals to 1 base case, and for I equals to 2 I am iterating and storing the prefix sum for I, and also for dp I am running the second floor division loop, and this count will be the max total number of counts that x by z equals to sum I, and this can easily here it is j, x by n is equal to j. So here we can simply get in the counts x by j minus I by j minus I by j plus 1. This will give us the counts of the different x that will be that for which the dp j will be same different x. So simply I am summing the dp I and multiplying dp j with the total number of counts. Total number of counts means for I, simply for that much values of j's, I only have to add dp 1 into counts of ones, which is 13 divided by 3 for dp 1 for dp 1 13 divided by 1 minus 13 divided by 1, and 13 divided by 1 plus 1 equals to 2, which is simply 13 minus 6 equals to 7, and we can see 13 minus 6 equals to 5, 5 not 13 minus 6 actually 7. So 1 2 3 4 5 6 7. So simply that for dp1 equals to 7, we will add in our dp I, which is for the 13, and similarly we will iterate for the others j's up to square, and for the unique values we can simply get it by I by j for the, and here is the edge cases for j greater than 1 we have to only consider, because we cannot divide it by its one divisions. Means if j equals to 1, we going to count it again that we have already counted here. And again I am updating the prefix sums by prefix of I plus prefix of dpi. So this is the simple case of these problems, and again move to the difficult ones, and pretty sure the difficult will be too easy for you. So for the hard version, we only have to observe that the first equation is transition is simple, that it could not affect, but the second one which we are running in square root times giving us the TLE, because here the n is large. So what we can do here is this from floor here, this floor expression, we can observe that the some particular dpi that we are getting in each steps have only contributions to some particular ranges, means for different y's. So instead of getting the say dpi and dpj here, and first I will draw it like that and I will explain. Means let I will be, we have to find dpi. So in the previous step we are running the loop for the j equals to 1 to j equals to 1 to square root of I, and getting the dpi contributions to the I, dpj's contribution to the I, and summing it. And in this we can do in this way. First we will, instead of, means if we are getting anywhere dpi, we will prefixly update all the upcoming further ranges that I can dpi have there its contribution to the further ranges. So how can we do this in optimized way? Since that dpi only have the contribution to I into x and this, so this will be something like range sum query. So we can also easily implement the range sum query in linear times. See how in this problem, move to the solution. First, for the fractional part range sum query, I am declaring another vector fracs, which will be store the floor divisions contribution in our dp's, and this will be simply our base case, and I have previously explained this will be contribute as the prefix sums. And as we know, in the range sum query there is some, for the particular range low and high, we add something x and add something minus x to the index high plus 1 if we have to update the range low to high. So here we are going to implement the same, and for each and in traveling we only adding x, so x will already going to be added in each transition we are doing here. So now first we will add the dp i's fraction contribution till I, and we will add the prefix some dpi's that we have done in the linear, that the first transition we are going to do choosing y from 1 to x minus 1. This will be maintained for this. And now come to our, this will be harmonic in nature because as the value we are getting for the y equals to 2 to something, so first y will be y will be of, means first I divided by something 1, I divided by something, means 2 divided by 1, 3 divided by 1, n divided by 1, 2 divided by 1 plus, 2 divided by 2 plus 2 divided by 2 plus 2 divided by, 3 divided by 2 plus n divided by 2, 1 here it will be 1, and 1 divided by 3 plus, you have seen this in prime, we are good when we are doing the prime factors, sieve of Iractose. Sieve of Iractose, you have seen this will be of logarithmic time, and here we are simply getting the low and the high of the particular ranges, and we will go till the low will not exceed n, and we are taking mean here to bound the boundaries of high, because it can be possible that the low will be less than n and high will be something n plus 5. So we only have to take till n as a, we declare our vector till n, so it not give segmentation fault, and simply I am doing here the range query, adding fracs, adding dpi and subtracting dpi to high I plus 1, and this will be for the first transition that we are going to add, and simply here the modular expressions, and this will going to be accepted because it's harmonic in nature, and the time complexity for this is n of something, n of log n, log of log n, harmonic nature, so it will be log n. So n for this and the log of log n for this, and this all for this video. We will meet in the next further problems, and I will be upload the solution in the descriptions, so you guys can take help, and thank you for the all.